Hello, and welcome to Team 1's final presentation. The team consists of Ethan Vanderroost, Jaden Manisto, myself, Oscar Roden, Quinn McIntyre, Sean Delaney, and Tate Matthews. Our chosen product for redesign is a manual pasta maker. A pasta maker consists of several key components: a sturdy frame, adjustable rollers, interchangeable cutting attachments, and a crank handle. Most of the components are made with stainless steel. The rollers, which can be set to various thickness levels via a gear mechanism, flatten the dough uniformly as it passes through. Users turn the crank handle to actuate these gears. Once the dough is flattened, cutting attachments equipped with sharp blades slice the dough into specific shapes, such as spaghetti, fettuccine, or lasagna. The entire assembly is typically constructed from stainless steel, providing durability and ease of cleaning, and giving the device a professional appearance.
We have identified two key customer groups. Our primary customers are food chefs and food enthusiasts. These are people who value quality homemade pasta, but do not require frequent use. Our secondary customers are small restaurants, cafes, and catering businesses that want to create homemade pasta for large quantities of people. However, they do not have a demand for an industrial-grade pasta machine.
Here is our fast diagram outlining the basic functions and sub-functions of our pasta roller. The main functions are to roll pasta, cut pasta, prevent slip, assure dependability, assure convenience, enhance the product, and please senses.
Based on our fast diagram, we created a function differentiation table. The functions that vary between different customer groups include customization, enhanced portability, and pressure distribution.
Here's the component commonality table with the modules that correspond to the varying functions. The turning handle corresponds to the customization function, and the base block and base plate correspond to the enhanced portability.
The first design for home chefs got rid of the vice grip at the bottom, replacing it with a larger base. This makes it more portable and easier to set up. The second design is for our secondary customers, small businesses. This design has a longer handle, allowing them to get more torque output to turn their pasta, allowing them to speed up production and turn a wider variety of dough.
Here is our product family design assembly sequence. This is how the design assembly varies between the original and modified assembly sequences. The modified assembly sequence utilizes the same first three steps before diverging for base and handle assembly.
For the module components, we chose the turning shaft, turning gear, and turning handle. These components are used to flatten the dough into uniform sheets. Their function is to adjust thickness, ensure precision, enhance the product, and please senses. Although the manufacturing cost of these components is relatively low, they can be redesigned to reduce assembly time and improve the overall function of the pasta maker. These are the components that came with the original pasta maker. The original gear is threaded on the inside, and the turning shaft is asymmetrical and threaded. Assembly time for these components is high because the threaded gear must be hand tightened onto the shaft during assembly. The total assembly time is 22.43 seconds. Here are our redesigned components. The first idea we had was to remove the threaded features on the parts. This improves the function of the product because the gear could move laterally if vibrations or a high amount of torque causes the gears to move laterally on the shaft. Beginning with the turning gear, a filleted key was added. This provides a locating feature that makes it easier to install the part onto the shaft. By introducing a key and slot mechanism to install the gear onto the shaft, we were able to make the shaft symmetrical, saving assembly time. We also hollowed out the turning handle, which reduces our material costs. The gear is constrained by a pin. We received quotes from Hubs.com on these redesigned components, and they reduce our CNC machining costs by approximately 40%.
For the platform parts, we chose rollers 1 through 4 along with the gears that drive them. These components are used to cut through the dough into various patterns. Their function is to distribute pressure, provide customization, and to please senses. Although the manufacturing cost for these parts is relatively low, the assembly time is high relative to other parts, hence why we chose to analyze these parts. Here's the picture of one of the rollers and gears. The ends of the rollers are threaded for the gears to be fastened onto, which takes a lot of time to assemble. We redesigned the rollers using the principle of DFA 13, avoiding adjustments, and DFA 4, allow for hand and tool access. The part function is easier to assemble as the gears are constrained laterally. The manufacturing cost by removing the threaded features is minimized and the assembly time decreases. Along with this, we used principle DFA 11 on the gears to provide locating features. The assembly time total with the fasteners is 64.92 seconds.
The base subassembly was chosen for redesign for automated assembly. In the function component mapping matrix, all four components, the base block, base plate, vice frame, and vice handle, share the same functive of securing the unit. This suggests a high potential for part consolidation. This would simplify the design and improve efficiency. The components were in the bottom right quadrant of the quad chart, indicating a high functional importance but also a high assembly cost. This is the subassembly of our base before redesign. As one can see, the vice frame and handle are connected to the base plate to complete the assembly. The total handling and insertion cost of the assembly prior to redesign was $7.75 per part. The assembly time is 5.1 seconds. Our modified design for the base subassembly improved our automated assembly time. The design changes include removing the vice parts of our subassembly and increasing the size and mass of our base plate. We are removing the fasteners that connected the base plate to the base block and replacing it with a chemical adhesive, making assembly quicker. The holes in the base plate are now longer, making fastener insertion easier and more stable. To improve automated feeding, the entire assembly is symmetrical on both sides of the Z-axis. There are no major changes to the product function. It still secures our unit to a table or flat surface. The manufacturing of our costs marginally decreased. This was due to less material costs for the base block and a reduction in parts. The total cost of our assembly increased from $7.75 to $8.30. However, the assembly time of our subassembly decreased from 5.1 seconds to 2 seconds, a 61% decrease in assembly time.
The first part we chose in the process selection was the base plate, which secures the pasta maker. The base plate is 205 millimeters by 135 millimeters with a section thickness of 3 millimeters and a dimensional tolerance of plus or minus 0.15 millimeters. Dimensions and location of the holes are important because they must align with the base block. The base plate is going to be made out of ABS plastic. Based on the shape, mass, thickness, tolerance, surface roughness, and batch size, we determined machining and injection molding to be viable candidates for our manufacturing process. We decided to go with injection molding.
First part redesigned was the base plate, which serves as a surface protector, ensuring the metal base does not chip any countertops or tables the pasta maker is used on. As seen above, as per DfM Pro rules, there were issues regarding the uniform wall thickness as well as minimum draft angle when injection molding. The operating cost for this model is 2 cents. The mold cost is $1.72, given the production volume of 50,000. And the material cost is $2.50. The sum of these costs is the total cost of injection molding for this part, which is $4.24. The base plate was modified as per DfM Pro guidelines. First, the wall thickness was reduced and made constant throughout the plate to be 3 millimeters from 10 millimeters. This decreased lowered material costs. Additionally, draft angles were added to increase manufacturability. These draft angles were 5 degrees along the exterior edges and 1 degree for the holes as suggested by DfM Pro. The operating cost for this model is 2 cents. The mold cost is $1.70 given the production volume of 50,000 and the material cost is $1.29. The sum of these costs is the total injection molding for this part and is $3.01. This represents a 40% cost reduction from the original design production cost.
The second part we chose in the process selection was the base block, which also secures the pasta maker. The base block has a thickness of 50 millimeters and has a dimensional tolerance of plus or minus 0.15 millimeters. Dimensions and locations of the holes are important because they must align with the base plate. The base block is going to be made out of aluminum alloy. Based on the shape, mass, thickness, tolerance, surface roughness, and batch size, we determined sand, dye, and centrifugal casting, along with forging, sheet forming, powder methods, and conventional machining were all viable candidates for manufacturing processes, but we decided to go with conventional machining.
The second part redesigned was the heavy base plate, which allows the pasta maker to sit on the countertop rather than being attached by a vice grip. This part must be machined as it is made out of a steel block. As per DfM rules, there was an issue regarding the small deep holes while machining. The deep holes would pose an issue for chip removal while drilling. Additionally, the team decided the sharp corners could pose a safety risk and as a result would need to be fillet. In order to fix these issues, 5mm radius fillets were added to the four corners of the design and the holes were made larger. The material cost for this design is $10.68 and the machining cost is $2.86. The price is the same as that of the pre-DfM design, as both parts have the same dimensions and require the same steps for milling. A price extrapolation was done based on the hub's prices for 1, 5, 20, and 50 units. The price was extrapolated to 50,000 parts. Additionally, a 20% profit was assumed and to be taken off of the manufacturing cost for the pre- and post-DfM models. The hub's price before the DfM is $9.22, and the DfM redesign was $9.11. This is a 1.21% reduction between the two models.
We created a product service system to improve customer experience and reduce environmental impact. To reduce environmental impact, we source product materials ethically and sustainably and recycled parts at the end of life. To improve customer experience, we create a rental program so customers can test the product to their liking, a warranty program to repair and maintain defective products, and an online feedback forum so customers can provide feedback on the product.
After our design for assembly, we reduced the manual time for the platform by 9.6 seconds and for the module component by 2.4 seconds. For the automated portion of our assembly, we saved 3.1 seconds per assembly. For our base plate, we saved $1.23 per part using design for manufacturability. And for our base block using design for manufacturability, we saved 11 cents. Some of the critique about our work is that the design is heavy and that we should aim to reduce parts in parts other than the base. Furthermore, we could do some additional DfM for the parts that we did not select for this presentation.